Our next presentation will be done by Shawn or Sang-Wook Kim. He's going to tell you about how to make your cloud Postgres faster.
He will tell us about how to make Postgres run faster on cloud.
Okay, thank you. Hi, I'm Sang-Wook. I'm from South Korea, and I think I'm the first Korean at this conference, right? Thank you. Not many people is here, right? Can you invite your friends to come here? I want more. Okay. So, who is using cloud? PostgreSQL on cloud. Not everybody. Okay, don't leave because I have some results on premise environment. Don't leave, okay? So today I'll explain what's the main difference between physical storage and cloud storage, and how this cloud storage affects PostgreSQL performance. So unlike physical storage, cloud storage is fully controlled by software, not by hardware, and you need to pay like for IOPS. You don't purchase full hardware, right? You need to pay for IOPS or throughput and capacity. So this makes huge difference from physical storage. So let's take a look at how AWS storage works as an example. So this graph shows storage throughput and latency as the I/O request size increases. So as you can see in this figure, the I/O latency is really similar regardless of the request size, right? 4 kilobytes I/O and 128 kilobytes I/O shows similar latency. But the problem is the throughput is totally different. And this is pretty obvious because we buy 3,000 IOPS for this example. So IOPS is fixed to 3,000. So what you can get from this storage is just simply, you can calculate simply like if you issue 4 kilobyte I/O, then times 3,000, that is what you can get, right? And this is because AWS EBS, storage, considers the IOs up to 256 kilobytes same. So 4 kilobytes and 128 is same, consume 1 IOPS in your IOPS budget. That's why this thing is happening. And this weird thing happens for like hard disk based storage on AWS. So the common knowledge when you use hard disk is random I/O is really terrible, right? Compared to sequential I/O, but it's not true on cloud storage. So this graph shows the storage throughput in megabytes per second. So there are two patterns like sequential and random for read and write. So as you can see, there is no difference between sequential and random I/O in terms of throughput, even for like read or write, it's identical, right? And also it's same for latency. As you can see in this figure, the latency for like sequential or random is same. You can test by yourself because it's on cloud, public cloud, so you can buy this volume and you can test by yourself using like FIO or whatever tools you familiar. So the main reason behind this result is that there is no mechanical part. Even though AWS says it's a hard disk drive storage, but it doesn't have the mechanical head So there is no penalty for random write or read. That's the reason. So in order to illustrate how this kind of thing affects PostgreSQL performance, I tested using PGBench on AWS. So this is the test setup on AWS. I launched two virtual machines on AWS Seoul region because I live in Seoul. It's more closer. And I located two virtual machines in same availability zone. So for client machine, I use R5 X large machine, which is equipped with 4 cores and 16 gigabytes of memory. And for PostgreSQL servers, I used the R5 the 4X large type, which has 16 virtual cores and 128 gigabytes of memory. And for this test, I used NVMe SSD directly attached to the physical machine hosting this virtual machine, and also use 1000 IOPS SSD volume as a storage. One thing to note here is that I did some basic tunings based on the PGTune, the website. You already know this, right? So I use this configuration otherwise noted. So let's take a look at how PostgreSQL performs on NVMe SSD. And it's pretty obvious, right? So PostgreSQL easily can fully utilize NVMe SSD like this. So this graph shows the storage throughput during the PGBench run. So the first phase is data loading, right? So data loading phase, and after that, I ran the TPCB like the benchmark, which is built in PGBench. So the storage throughput is saturated to 250 megabytes, around 250, and the final result is 13,000 TPS. Okay, but actually, this the SSD volume is the same size of the NVMe SSD, 300 gigabytes. But as you can see, the PostgreSQL cannot fully utilize the underlying cloud storage. So when I loaded data, it's PostgreSQL somehow utilize better the cloud storage. But when I ran the PGBench, PostgreSQL only can get like 20, 30 megabytes per second from this type of storage. So the final result is 1,000 TPS, and which is like more than like 10 times more throughput, transaction throughput, right? This throughput because unlike NVMe SSD, PostgreSQL cannot utilize the underlying bandwidth. So this graph shows I/O size and the storage IOPS during the benchmark run. So the calculation is really simple, right? The IOPS is fixed to 1,000, but throughput is the throughput that this storage can provide is much more higher. Actually, for this type of storage, it can provide 250 megabytes per second, up to 150. So throughput is just the requested I/O size times 1,000. That's why when I ran PGBench, there are many small writes, random writes. So, for example, if PostgreSQL issue 8 kilobytes write, then it can get only 8 megabytes per second, even though this storage can provide 250 megabytes per second top. So what's happening inside? So in order to fully understand what's going on, we need to look into inside Linux. And it's similar to, I mean, it's almost same for like other OSs. So the main reason behind is that the I/O unit from PostgreSQL and even from Linux is really small. So PostgreSQL issues I/O based on like 8 kilobytes, right? 8 kilobyte unit. And Linux, the basic unit of I/O size in Linux is 4 kilobytes. So when PostgreSQL writes the dirty data to Linux kernel, it writes in 8 kilobyte unit, right? And it's first buffered into Linux page cache. And after that, when PostgreSQL issues fsync or fdatasync, it should go to storage, right? So internally, Linux writes out all the dirty pages to storage, and between the page cache and storage, there is file system which handles the block mappings, and because basic unit in Linux kernel is 4 kilobytes, so the process or threads issues in 8 kilobyte unit to storage. But in order to merge adjacent blocks inside Linux kernel, block layer try to merge adjacent blocks. So it will look like this. But the one problem is that even though the PostgreSQL issues writes in one big chunk or 8 kilobytes, file system can allocate in 4 kilobyte units. So it may not be sequential because of file system, because file system allocates in 4 kilobyte unit. So final result is, for this example, the Linux should issue 8 IOs to storage, right? It means it consumes 8 IOPS in your IOPS budget for this for the cloud storage. So actually, I really try hard to tune the PostgreSQL performance to match the performance on NVMe SSD. So I try first tune the checkpoint, the frequency, and the write back frequency inside Linux. So I changed the max file size to 128 gigabytes and checkpoint timeout to 30 minutes. So this setting guarantees that there is no checkpoint due to the max file size. Only happens in 30 minutes interval. So by tuning these parameters, we can get like 30% better TPS. Okay, so during the test, I found that even though the data set in this case is full, the working set is fully populated in memory, PostgreSQL shared buffer plus Linux page cache, but while file sizes grow up to around 60 gigabytes. So the WAV files and data files contending for cache space inside Linux. That's why even though data set fits in memory, there was read IOs for reading data, because while writes, the push out the data files, data blocks cached in Linux. So in order to alleviate this problem, I used huge pages, because based on the analysis for this test, PostgreSQL use like 8 gigabytes of page tables, because PostgreSQL implemented as multi-process, so that means one process needs one dedicated page table. It's not same for multi-threaded application like MySQL. So but we can reduce this impact by using huge pages, so that I could get like 20% more throughput by using huge pages. And actually, I did many tunings, not only for this, but the final result, the optimal performance I could get is this, like the green bar, the 1500 TPS. So maybe a possible solution for the AWS storage is that making the basic unit of I/O to 256 kilobytes. So if we can somehow change this, then we can issue just one I/O instead of 8, right? But it's not true for like physical storage. If bandwidth is kind of limited, then we end up with wasting some bandwidth, right? Because clean pages or clean blocks also need to be written to storage, but it's kind of valid for cloud storage. So, but bad news is that even if we can somehow make the I/O unit more bigger, it's only work on AWS EBS type, because there are many vendors, right? Not only for only AWS. There are Google Cloud, Azure Cloud, and I checked that Yandex Cloud or Alibaba Cloud. There are many vendors, so it's not easy to tune. Get optimal performance for each type of cloud, each cloud and each storage type. And even for one cloud vendors, there are many types of storage, and each storage has different policy and different pricing policy, and the guaranteeing, the way of guaranteeing IOPS or throughput. And some storage types has kind of burstable feature. And actually on Google Cloud, they support 16 kilobytes atomic write already. So if you need to write atomically, on your application, you can rely on this type of storage. And in Azure Cloud, there is 4 types of block storage: ultra disk and standard premium SSD, standard SSD, and standard hard disk drive. And all these 4 types of storage have different policies. So in order to handle this problem, this situation, we are building a file engine called AppOS, and it's implemented as an extension, and it's specially built for support diverse types of storage. So as you can see in this figure, this is just this extension, so it can run on any type of environment, bare metal machines or virtual machines, or even on inside container. And it currently supports physical hard disk, SSDs, and AWS storages, and Google Cloud and Azure. So when we first designed this extension, we kept three goals in mind. So the first thing is we don't try not to modify PostgreSQL codes, because we modify the PostgreSQL, that means we are making a new database, right? And actually our team is not, are not experts of like database development. So we need to focus on what we can do better. So we decided not to fork PostgreSQL, just implement it as an extension. And so PostgreSQL has, second one is PostgreSQL has unique needs for file IOs, right? So we, this AWS extension should provide like PostgreSQL aware IO processing. And the final one is, as I explained before, there are many types of storage, and each type of storage has different characteristics. So AWS should aware the storage internals to get optimal performance. These are 3 goals when we designed the AWS extension. So this is architecture diagram of AWS. Basically, AWS extension is just a collection of libraries. So at the top, in order to work transparently without modifying PostgreSQL, we intercept system calls. So we have system call handler library, and the main role of this library is intercept system calls and emulates like signals and all things. And the next part is the PostgreSQL adapter. The main role of this adapter is extracting the internal information, like which process is which, like which process is a backend process and checkpointer, vacuum workers, and stats collector, something like that. And also which file is which file is WAV file or data file, something like that. And it passes down that information into the AWS core. And inside AWS core, we have virtual file system layer and page cache file mapping. Actually, file mapping is more like file system, but it's not full file systems. And at the bottom, we have IO engine to issue IOs based on the underlying storage characteristics. So this is the whole architecture. And so in order to use this extension, you need to specify which environment you want to deploy your PostgreSQL, like AWS or the on-premise or Azure. You need to specify storage type like EBS, IO1 or GP2, and the Azure Premium SSD, standard SSD, something like that. Then the storage optimizer module will translate that information to reconfigure inside the AWS. I will explain this more later, okay? Before going into the deep internals of AWS, I will show some benchmark results using PGBench. So this is a test setup on AWS. So I used R5 X-Large and R5 4X-Large, similar to the setup I explained before. And I used 1,000 IOPS, the SSD volume, for this experiment. So with AWS extension enabled, PostgreSQL can process 19 times more transactions. So basically, without AWS, PostgreSQL can only process 1,000 transactions per second, but with AWS, PostgreSQL can process 23,000 transactions per second. And latency is also improved. Improved a lot. So average latency and deviation is more stable than without AWS extension. In order to why the AWS can get the better performance, this graph shows the storage throughput. So red dots indicates PostgreSQL, and blue dots indicates PostgreSQL plus AWS. enabled. So as you seen before, so without AppOS, PostgreSQL only can get like 20 megabytes, 30 megabytes per second from its EBS storage, but with AppOS enabled, PostgreSQL can get like 250 megabytes per second when it needs to do heavy IOs, heavy writes in this case. Okay, so the next one is test on Google Cloud. Yeah. Yeah. So when PostgreSQL does checkpoint, it needs lots of IOs, right? And when checkpoint finished, there is not much IO to do just while logging. So that's why the throughput goes down, because PostgreSQL doesn't require that much. Okay. So this setup on Google Cloud, so I use N1 high CPU, 8 types of machine, and it has 8 CPUs and 7 gigabytes of memory. And I use this machine as a client. And for server, I use 32 cores and 120 gigabytes of memory. And as a storage, I use 500 gigabytes of SSD. So on Google Cloud, the AWS can make PostgreSQL process like about 4 times more transactions per second. So actually the reason behind this is that similar to the results of AWS. And the last result on cloud is Azure Cloud. So I use similar configurations for testing, and for the storage I use 256 gigabytes of premium SSD. So on Azure Cloud, PostgreSQL can process like 800 transactions per second, but with AWS enabled, it can process 9,000 transactions per second. Many companies these days adopt cloud. There's still lots of on-premise environments. So I tested on-premise with physical NVMe SSD. Actually, it's not. The whole environment is not on-premise, but the storage is physical storage because AWS provides like the directly attached NVMe SSD as an option. So for this test, I used R5D type of instance and used 300 gigabytes of NVMe SSD as a storage. So not that much compared to other on clouds. But AWS can make PostgreSQL process more than like 2 times transactions per second with NVMe SSD. So okay, so let's look into more details of AWS. So in order to work transparently without changing codes, the first layer is system call handler, syscall handler. So it basically we can register pre-hook or post-hook for each system calls. So we register the file-related system calls like open, read, write. We register hook for open, read, write, and many other file-related calls like stat, appstat. So when PostgreSQL first calls file-related system calls, it does not go directly to Linux kernel. It goes to our layer first. And since the VFS layer abstracts all the file-related stuff, so we can provide POSIX file interface like just open, read, write. That's why we can seamlessly integrate with the existing applications. So inside VFS, we have inode structure, the entry, the cache, iCache, and the FD map, and context. And it's really similar to Linux kernel internally. And last part is because we need to distinguish the which layer PostgreSQL process currently reside in. We added kind of virtual ring. So similar to like the user level to the OS switch. So application running on ring 3, right? And the OS should run on ring 0, so that OS can issue, the execute privileged instructions, right? So we added the virtual ring. So PostgreSQL run on ring 3 and the AWS ring on ring 0. And we use this information to correctly handle signals. So the next part is PostgreSQL aware I/O processing. So when file related system calls issued, it's intercepted and it directs to the PostgreSQL adapter, and it takes kind of I/O priority and classify file types and the page size in order to match to PostgreSQL page size, which is 8 kilobyte by default, right? And also the while write is really important for like the OLTP style workloads. So we pre-allocate while file. So we maintain the while file pool. So when there is a high peak of writes, we can use the pre-allocated while file. And inside AWS, the page size in page cache is matched to the PostgreSQL buffer page size, which is 8 kilobytes by default. And we set we have concept of logical sector and logical blocks. So actually in physical environment, the sector size is 512 or like 4 kilobyte, right? That's why PostgreSQL cannot rely on the atomicity, because the atomic unit should be 8 kilobytes, right? Because the PostgreSQL page size is 8 kilobytes. So in our file mapping layer, we guarantee this 8 kilobytes is not, the atomicity of these 8 kilobytes. And the bottom layer, IO engine issues IOs based on the configured priority. So for example, backend process can have more higher shares priority compared to like checkpointer or vacuum workers in order to stabilize the transaction latency. Okay, the final part is about storage aware I/O processing. So as I explained a little bit before, so we have storage optimizer module. So it gets the spec from user, the infra type, storage type, and storage capacity, storage IOPS, and storage throughput. And these things, you need to know these things anyway, right? Because you're gonna provision your storage on cloud when you provision your storage on cloud. And for like the physical SSD, you don't need to specify like IOPS or throughput. It just automatically set to the kind of the general value. So based on these specs, the storage optimizer set like how many IO workers should run on this system based on the number of cores and the logical block size. This logical block size is the basic unit of doing IOs inside AWS. And in order to increase parallelism, we do something like file sharding. So each IO worker dedicated to specific file range. And so based on this configuration, I/O engine will issue the I/O based on the logical block size. So for example, on AWS, 1,000, if you provision 1,000 IOPS, the logical block size will be 256 kilobytes, okay? And actually the local, there is a kind of local SSD, directly attached to the host machine, which the hosting the virtual machine, and this type of storage is common for all cloud vendors. But the problem is this storage, you cannot rely on this storage because there is no SLA and there is no replication. So if virtual machine shut down, then data will go away. So we are working on utilizing this local SSD as a memory extension. So we can use this local SSD as an extension of page cache. So we don't store the data that need to be durable, just used as a more like cache. And this is work in progress. Okay, so because this AWS extension is running between PostgreSQL and Linux kernel, it can work with the PostgreSQL derived databases, like including like Cyrus and Timescale and EDB and many other databases. Actually, I only tested Timescale and Cyrus and Enterprise DB. And for Cyrus and Timescale, you don't need to do anything further because that database is also implemented as an extension. But for like, for example, run with EDB, the advanced server, we need to recompile against the EDB header files and libraries because it's kind of fork, not compatible, fully compatible with the open source PostgreSQL, right? So I'm going to show you just only one result with Timescale DB. So I set up the test environment on AWS and used the M5.2x large machine, which has 8 cores and 32 gigabytes of memory for both server and clients. And I ran the time series benchmark suite, which is developed by Timescale itself. So I followed kind of the benchmark steps written in their blog. And I used 16 terabyte of EBS hard disk drive and 1,000 IOPS EBS SSD as a storage, and used the Timescale DB version 1.5. So this graph shows the data inserts throughput. So with EBS SSD, Timescale DB can process 160,000 rows per second, and with hard EBS HDD, it can process 86,000 rows per second. But with AWS extension, Timescale DB can process 230,000 and 260,000 rows per second for EBS SSD and EBS HDD respectively. And the thing I like to share is that for this kind of inserts heavy workload on AWS, maybe considering hard disk drive for storage is better because this kind of workload is more like throughput bound, and the 1,000 IOPS SSD only can provide 250 megabytes per second, but hard disk drive throughput optimized, the EBS hard disk drive can provide 500 megabytes per second. So that's it for today. So thank you for listening, and I'll take some questions.
All right, thank you. So does anyone have any questions? Okay. Дадите микрофон. Ладно, я дам.
Hi, at first I would like to say thank you for your great presentation. It's very impressive. Am I understand you right that this extension could be used on the EC2 instance in AWS? You can't use it for the RDS instance.
You can use, sorry?
Can I use it for this extension with RDS instance or just with EC2 instance in AWS?
You mean RDS? Yeah, actually, this is extension, implemented as extension. That means if AWS support this extension in RDS, then you can use, but you cannot access to that machine, right? If you are using kind of managed service. So for now, you cannot use it until AWS accepts as an extension for their service.
And one more question, sorry. Am I understand you right? Can you provide the result, your result that you show about the throughput and transaction per seconds? It's for OLTP workload, right?
Yeah, I ran PGBench, the built-in benchmark.
Do you have some numbers for ALAP workload for DSS systems?
Sorry, a lot.
ALAP, analytical, when you...
Yeah, okay. Actually, what AWS can provide is Excel for write-intensive workload, not read-intensive, like analytic queries. But AWS can help for like data ingesting. So it's basically optimized more for writes compared to reads. So if you have lots of writes, then likely you can get better performance with AWS.
Okay, thank you very much.
Thank you.
Вы показали сравнение с
So you showed a throughput comparison for two instance machine. Did you do any comparison for managed server?
You showed throughput on what?
You showed throughput on EC2 instance Postgres database. Have you did comparison with managed service?Maybe I missed that slide, or did you do comparison?
You mean the comparison results between the managed service like RDS versus...
Exactly, yes.
Yeah, actually we did that, and yeah, actually the RDS just use PostgreSQL internally, vanilla PostgreSQL, no modifications. So performance is really similar to just on EC2. And actually we also compared with Aurora. You know Aurora? With identical resources, we can provide better performance even compared with Aurora Postgres. Yeah.
All right, so does that answer your question? Okay. Any more questions? All right.
Okay, so one question. Did you try before building this to try to recompile Postgres with different page size? Like, because you can tune it to 256 if you want to.
Actually, this one, this benchmark used some kind of batch size. So the 10,000 rows are batched into one copy command for this benchmark.
Yeah, but I mean that the Postgres page size is 8 kilobytes, right?
Yeah, buffer size is 8 kilobytes.
Yeah, but you can change it. You can recompile Postgres and make it 256 if you want.
Actually, I tried that too, and the maximum size is, as far as I know, 64 kilobytes. Am I correct? 32, 64, maybe. So if you increase that number, then you can get better performance on like cloud. If data set, working set is fully fit in memory. because the increasing the PostgreSQL buffer page size is not always good because it pollutes buffer cache.
Yeah.
So if data set is not fit in memory, you will end up with like ping-ponging the files, because when select calls like access 100 bytes, it needs to read 64 kilobytes, right? And what if the remaining bytes are not used anymore, and the other client comes and read another 100 bytes, and it can contending each other. So that's why it's not easy to, I mean, it's not a good idea to like increase buffer size in PostgreSQL. And actually, maybe I forgot to explain. In AWS, we don't issue big read IOs to storage because it may pollute our page cache. So when we need to read, we read big size first, but it does not go to our cache, global cache. It goes to only process local cache. So if your pattern is sequential, it will hit in your local cache. But if your pattern is random, this cache is just go away without polluting the global cache.
Okay, and it's just a pure Postgres extension. Doesn't require anything else from the OS, right?
Sorry?
It doesn't require anything else from the OS. It's just pure Postgres extension.
Yeah, right. It only runs on Linux, not like FreeBSD or Windows. Yeah,
okay.
For now, yeah.
Sounds very good. Thank you.
Thank you.
Thank you. Okay, any more questions? All right.
Thank you, Shawn. Please clarify the status of the project. A quick glance, I thought it's beta, and I did not understand if it closed source or proprietary or what. Please clarify the status.
You mean closed source?
Yeah. Is it closed source or open source? And I've seen it's still beta.
Yeah, right. It's still beta, and it's not open source yet because it's kind of a bit risky, and maybe I can discuss with you about this because we already spent lots of time for making this work, and it's backed by company anyway, so it's not easy to open right away. But our plan is to open the core part, like the AWS core, right? We have AWS core. I think this part is really critical, so maybe it's better to open this part, and the remaining, the storage optimizer and PostgreSQL adapter, we can keep it in closed source.
Yeah,
that's our basic plan. Yeah, thank you.
Thank you. Okay.
How many people involved in your development and do you have some client used your product in production?
Sorry?
Do you have some clients used your product in production? And how many people are involved in your project as developers?
Yeah, actually, as I answered before, it's about to launch as a beta. And actually, we tested internally with Samsung SDS because they have some PostgreSQL clusters internally. So we show them like 5 times better throughput with the workload. But the problem is, actually, to be honest, it's not running on production because after the POC, we realized that Samsung, the critical system inside Samsung still rely on heavily rely on Oracle or other commercial databases, not PostgreSQL. That's why we couldn't find any real use case internally, so it's not used in production. And our plan is launching as beta release first, because we only tested internally and with several companies. So we really want to test publicly, and we're about to launch. I hope we can launch within 1 week, so you can sign up for beta through our webpage.
Okay, thank you.
Thank you.
Is that all? I think so, yeah. Okay, let's thank Shawn Kim once again.
Thank you.
And if you have any questions left, you can catch him and torture him with questions.